All right. Okay, so yeah, like an idiot, I forgot on my very last thing I did on the way out the office was I was going to put the calculus book in my backpack. And about halfway down here, realized that I was about 7 pounds too light. So if I'm looking at my phone, it's just because I'm looking at the textbook with little tiny words. So questions I can answer about homework from 11.1 and 11.2 first. Yep. Number 14. Could you remind me what it was? All right. Sorry, I use my computer, but it is otherwise occupied at the moment. So.
I have it. It's the sum from n equals 2 to infinity.
Sum from n equals 2 to infinity.
And then 8 over n squared minus 1.
Yeah.
Yeah.
Okay. I guarantee you that's a telescoping series, right? Because I have no idea how else to do it, right? There's no other attack we can make on this. You said this is number 14. Okay. So the trick we're going to use here is we're going to rewrite this as 8 over n plus 1 times n minus 1. And then we're going to use partial fractions to break it up. So again, why do I think to do this? Why am I suspecting this is a telescoping series? Well, by the logic of math books, we're in a chapter where we have no tools, right? We've got geometric series and telescoping series and nothing else. So by the fact that it's not geometric, the only other possible way we could do this is with some sort of partial sum thing, right? So, and the fact I can factor the denominator like also leads me to that conclusion. And maybe it even told you it was telescoping, I don't know. So this is a over n plus 1 plus b over n minus 1. There's a bunch of different techniques for how to attack this. So this is called partial fractions. So the way I'm going to do it is with the magic method. So it's what minus, you put in 1 here, which puts this a 2, so it's a 4. So this is positive 4, and this is negative 4. All right. Okay. If you don't know how to do that, you just multiply out and solve for a and b. It's the techniques we learned in the last chapter, right? So this is really the sum then from n equals 2 to infinity of minus 4. Actually, let's write it in the positive negative way. 4 over n minus 1 minus 4 over n plus 1. And now let's just start writing down some partial sum. See what happens. So S1 is 4 over 1 minus 4 over 3. That's 2. 4 over 1 minus 4 over 3 plus 4 over 2 minus 4 over 4. Now it would be counterproductive to simplify these things algebraically, right? We should just leave them unsimplified and hope that everything will cancel away. Nothing cancels yet. Let's keep going. S3, 4 over 1 minus 4 over 3, 4 over 2 minus 4 over 4, plus 4 over 3 minus 4 over 5. Aha, there we go. This cancels with that. S4, 4 over 1 minus 4 over 3, 4 over 2, 4 over 4, 4 over 3 minus 4 over 5, 4 over 4 minus 4 over 6. Okay, so the 4 over 3s are gone, the 4 over 4s are gone, and I'm going to assert, I believe now at this point that I see the pattern, which is everything is going to cancel except the last 2 terms and the first 2 terms, right? But now what we're going to get is, if I write the next one down, what's going to be left? Well, the next one should still have the 4 over 1 and 4 over 2, but the 4 over 5 is going to get eaten up, and there'll be a 4 over 6 and a 4 over 7 left over, right? So this telescopes, but it telescopes with extra pieces floating around in the end. Your numbers may differ if you don't have the 8 in the numerator, but the same idea is going to apply. The fact that the pattern is a little different here happens because these are separated by 2 instead of 1 in the example that we did in class last time. If you guys notice me make a mistake someplace or something is confusing, please stop me. I'm not perfect. Okay, so my assertion, what I believe, I'm going to write down a speculative theory for what Sn is. I think Sn is 4 plus 2 minus 4 over n plus 1. Have I missed by an index? I did miss by an index, didn't I? I'm an idiot. I missed. I jumped up by, did I miss? S1.
I think you started at 1.
S. Oh, I shouldn't have had this term in here. All right, let me. I didn't make a bad mistake. But let me fix this real quick because my formula is going to be incorrect if I do it that way. Sorry. Okay. Sorry. S2. I mean, okay. S1, S2 doesn't matter. S3, S4, S5. S2 is going to be A2, which is 4 over. Oh, this is. Why did I erase this? You guys shouldn't have let me do that. 2 minus 1 minus 4 over 2 plus. Made me think I made a mistake. You didn't make. I made me think I made a mistake. Okay. Then the sum of the first 2 terms is 4 over 1 minus 4 over 3. Increase the denominator by 1, and we get. Yeah. Okay. That's why I thought I made a mistake. So I thought. I hope nobody started erasing just because I did. 4 over 1. 4 over 3 minus 4 over 5. 4 over 1. I got worried there when my index pattern didn't match what I thought it should have because the n plus 1 and the n plus 2 didn't exist anymore. 4 over 4 minus 4 over 6. Okay. So actually, is everything gone? 4 over 1 is left. 4 over 2 is left. The 4 over 3s are gone. And the 4 over 4s are gone. And the 4 over 5 is going to get eaten on the next go. So Sn looks like 4 over 1. That can't be canceled away because they can never return. 4 over 2. And then this term is n. Right? I mean, that matches. S5 and S5 match. That's my speculation for what this pattern should be. Everything cancels in the middle, but we got 2 terms up in the front and 2 terms up behind because these are separated by 2 numbers this time instead of 1 number. Well, if I took the limit of that, what do you get? 6. 4 plus 2. That goes to 0. This goes to 0. So the limit is 6. It's typical of this kind of thing. And the only way you can make these even slightly tricky at all is to hide the telescope by making you write slightly more terms down in the partial sum sequence. Okay. What else? All right.
Be able to do number 7.
Number 7. Can you tell me what it was?
Yeah. Let's see here. It was the sum from n to infinity of -8 to the n minus 1 over 9 to the n.
Minus 8 to the n minus 1 over 9 to the n?
Yep.
All right. All right. So when I see powers of n, what's the first thing I think? Like what I'm looking at here is number 7. I see sum from n equals 1 to infinity of 8 to the n minus 1 over 9 to the n. What's the very first thing I should think when I see powers of numbers to the n? It's got to be, it's geometric, right? So Now I'm going to give you two ways of attacking a geometric series. You can try to manipulate this formula into the formula for a geometric series, or you could just write down the terms. Now, it's useful to get in the habit of multiplying these or of manipulating these things algebraically. So we know that the form we're after here looks like this. Right? This is the form we're after. We don't quite have that because there's this 9 to the n down here. And also these powers don't match. So if I want to put them together to the nth power, one way of doing that would be to rewrite this series as 1/9 times 8 to the n minus 1 over 9 to the n minus 1. Get one of the 9s and yank it out. Because once the powers match, I can combine these together. All I've done here is 9 to the n minus 1 times 9 to the first. You add the powers and you get 9 to the n. This is a typical sort of idea that we're going to be using in here, right? Is to manipulate expressions that are simplified by unsimplifying them in a very specific way. So this is some 9 equals 1 to infinity of 1/9 times 8/9 to the n minus 1. And now it's in the right form, and you can just write down what the answer is. It converges because R is 8/9. So this is a convergent geometric series. And what it converges to, yep. Is there a negative somewhere? -8. So this, like this? Okay. Not going to be much of a difference here. Still a convergent geometric series. Because the absolute value of -8/9 is less than 1. As long as the ratio is strictly between -1 and 1, you've got a convergent geometric series. And what it converges to is A over 1 minus R. So 1/9 divided by 1 minus 8/9. Now, the best part about this is that for me, simplifying that down into a simple fraction is arithmetic. So if you don't want to go any further than that, you just leave it. Right? It's hard to test your answer is correct if you do it this way, but I don't care if you go deeper than this with these exercises. Okay?
Yeah, thank you.
Yep.
Can we
Anything else?
Can we do 15?
Which one is 15?
1 second. Let me pull it up. It's sum of n equals 1 to infinity, and then cosine of 2 over n squared minus cosine of 2 over n plus 1, like quantity squared. The whole, like n plus 1. Yeah.
So that is just it's just a telescoping series. So this is what that's going to happen here is when you start putting the terms in, it's going to be another thing that we had before. So I'm just going to actually start writing down. You know, I think actually in this exercise it tells you it's a telescoping series, right? So let's just actually start computing some terms, right? So don't get tripped up by the fact that there's this cosine running around in here. S1 is the cosine of 2 over 1 minus the cosine of 2. Is it really n plus 1 squared?
Yeah.
It's not too. Again, it's going to be okay. So you're going to get. I'm not even going to do that. I'm going to write this. And S2 cosine of 2 over 1 minus the cosine of 2 over 2 squared plus the cosine, that right there is A1. Now you put in A2, and what you're going to get is the cosine of 2 over 2 squared minus the cosine of 2 over 3 squared. Notice no simplification needed. This is just a straight telescoping sequence, right? This term and this term are the same. So they cancel.
Okay, makes sense. Thank you.
And then Sn, there's only one thing you need to remember about this when you're done. So the first thing we're going to insert is that Sn is the cosine of 2 minus the cosine of 2 over n plus 1 squared. After you do all the cancellation, this result happens. Then you take the limit as n goes to infinity. The only thing you need to know is what the limit of this is. So what is the limit as n goes to infinity of Sn in this case? I'll give you the easy part. I take one part for me. This goes to 0 because you've got 2 over something tending to infinity, which tends to 0. So the inside of this tends to 0. And because we don't want points taken away from the problems around the problem, we remember that the cosine of 0 is equal to 1. So this whole thing tends to 1. See, this is just the answer. No simplification possible. Anything else? All right, let me close my Chrome here so that my brother's chatting me doesn't keep beeping. Okay, what else? All right, let's do the integral test. I'll remind you that the homework is actually due, like, quote unquote, due today. So you should try to get it done by tonight, just so you're not behind going into the weekend. All right, so 11.3 is about the integral test. And so the whole point of the whole next part of this chapter is that most of the time we don't know what a series adds up to. We just need to know that it adds up to something, right? That's the game that we're trying to play here, is how do we know when a series converges? So far we've looked at geometric series. And we've looked at telescoping series. And we've looked at the definition of a convergent series, but there's a lot of series that come up all the time that these don't work on. So the prototypical example of a series that we would really like to know converges is this. What about 1 over 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared, and so on. This series pops up all the time in physics, for example. And it was a fundamental question of mathematicians a couple hundred years ago, if this series adds up to anything. If you start doing computations of the partial sums, it looks like it converges. It looks like it converges to a number. If you actually start computing this numerically and adding it up, it looks like as the terms get piled on the end, it settles down to a number. Actually, does anybody know? Is there anybody here that knows what this is off the top of their head? You got the reciprocal of the answer. So yeah, this is famously equal to pi squared over 6, which is not what we're going to be. I'm not going to do this proof, but it does add up to this number. One of the first genius moves of Weierstrass was to figure out that this existed. Right? There's a really clever argument you can clever but wrong argument you can use to show it. So the idea is, okay, now with the benefit of hindsight, we know that this series converged. But if you're a mathematician 200 years ago, or you're just stumbling around with a numerical series, how do you know it actually converges? So what they noticed, what mathematicians noticed, was that this particular series could be approximated by an integral. If you draw these dots, let's just say we graph the sequence. Graph the sequence. 1, 2, 3, 4, 5, and so on. And I'm going to exaggerate the distance between points here. I'll put 1 right here. The sequence A1, A2, A3, A4, so AN is equal to 1 over n squared. If you plot this like it was a function, you get, it starts here at 1, and then it's 1/2, and then it's 1/3, and then it's 1/4, and then not 1/4. I'm talking about not even 1/2. It's a fourth, right? 1, 1/4, 1/9, 1/16. It's square. As you go on, you square the index, right? So one idea that you have when you're looking at this is, well, okay, I don't know what this sequence adds up to, but notice that the curve that these all sit on, the graph that these things all sit on, is f of x is equal to 1 over x squared, right? And notice that any estimate of the integral of this thing, okay, so we're going to do all kinds of math together here. Stuff from the past. Can you guys remember what this is? Now, I don't need to know the exact number. I just need you to remember, does that make sense or not? There's an improper integral because there's an infinity in it. You should have talked about this in your calculus 2 class. Does that converge or diverge as an improper integral in calculus 2? Why?
I remember it when you write the limit, you see in the up and down.
Okay. So if you actually do this as a limit, if you rewrote this as the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx, this turns out to be a number that exists. And if your professor was good at this particular section, they would have also told you that this number right here dictates when these integrals converge or not, right? If there's a number larger than 1 attached to the x down here, this integral converges. Now notice that this integral is bigger than all of this stuff if I treated it like it was an area. If I treated this series like it was an area, I could think about rectangles here that look like this. Because multiplying by 1 keeps things the same size, right? So if I treat this series like it was a height 1 over 1 times a width 1 plus a height 1 over 4 times a width 1 plus a height 1 over 9 times a width 1. I could think of this series as being represented by a bunch of rectangles that sit underneath this graph, right? Like I can think of this as an area. So one of the things that you would have learned in that class is the Squeeze Theorem. So I have a function whose area exists as I tend to infinity. And I have another function trapped underneath it, another area trapped underneath this thing which converges. So if the area underneath this is finite, what does that say about the area of these rectangles? So the areas are stuck. These areas are bigger or smaller than the area underneath the curve. They're smaller, right? They're underneath, they're inside, they're trapped above by the function. So what we're going to say is, well, because the rectangles are underneath the function, and because the function area exists, then that means that the sum of 1 over n squared has to be less than the integral of 1 to infinity of 1 over x squared dx. They're not equal to each other, right? Because the rectangles cut these big pieces off. But the idea is if I think about this like an area, it's stuck underneath this area. But this was finite. So if this is smaller than this, but it's finite, then that also has to be finite. That make sense? So that right there, this idea that I could study if this adds up or not by looking at this integral, that's the core of the integral test. The idea is I think of a series as a collection of areas of rectangles, and if I can measure them, if I can find a function that sits above all those rectangles and the area of the function is bounded, then the series must have also been bounded. So this is convergent. All right, this is convergent because of this line right here. Sum from n equals 1 to infinity of 1 over n squared is less than the integral from 1 to infinity of 1 over x squared dx, but this was bounded, which means this was bounded. So this converges. All right, so now we're all tooled up and we think, okay, I'm going to tackle the problem and show that it's convergent. What about this series? We say to ourselves, okay, 1 over root 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4. I'll plot that guy. I'll see if I can find a function that makes me believe this converges or not. 1 over root 1, 1 over root 2, 1 over root 3, 1 over root 4, 1 over root 5, and so on. Still asymptotic to 0, but passes the test for divergence. It could converge. What function sets out the boundary of this sequence? Not 1 over x squared this time. Okay, I'm testing your knowledge. If we had 1 over x squared, this integral existed, right? The integral from 1 to infinity of 1 over x squared, that was an integral that existed. So the first thing we're going to do is we're going to say, well, how about this? Why not?
Because the power of it is less than 1.
Because you're less than 1. If you integrate this, what happens is the root x pops to the top, and then you're taking a limit as something that goes to infinity, but you're plugging infinity into it. So this is a divergent integral. It's a divergent improper integral. And what we're going to do is we're going to say, well, look, another way of estimating the area of this series is to put the boxes here. I mean, I can estimate what the box is however I want, right? So I'm going to say, oh, well, ignore this one for a second. All right, so I put the ones here now, right? Think about the rectangles as going this way, that this sequence is measuring this area of rectangles. But notice this green area is larger than an area that runs away to infinity. If I think about the sequence as representing the area of a bunch of rectangles, the area of these rectangles is bigger than the area of this integral. The area of, say, the not a green chalk now, but these green rectangles is larger than the integral from 1 to infinity of 1 over root x dx. But this is infinite. If this is infinite and that area is larger, can that series possibly add up? The answer is no, it's bigger than something that's infinite. So this is a divergent series. Now you might say, okay, well, you cheated because you shifted the rectangles from one to the other. Why does that work? All I have to be able to do is show that it happens once. If I can interpret the series as an area that's below a finite integral, then the series must be finite. And if I can interpret the series as an area that's above an infinite area, then it must diverge. Okay, I just need to do it one time in order to have that work. So this is a divergent series because it's larger than a divergent integral. This is what we mean by the integral test. So I'm going to formally write down the definition, but this is where it comes from. Before we get there, I'll note that because of the behavior of what we did right here, where we did the squared power and we did the 1/2 power for the series, works for any power p except the power of 1. So a series of the form 1 over n to the p, where n runs from 1 to infinity, this is called a p series. So the ones we've looked at so far, we looked at the harmonic series. And that's the one where p is equal to 1, right? 1 over n was the harmonic series. We looked at that last time. And we just looked at the sums of reciprocals of squares. That was n equals, sorry, p is equal to 2. And we looked at the reciprocals of square roots. Just now, that's p is equal to 1/2. So the series we just did is the p series of p equals 1/2. Harmonic series, divergent or convergent? Permanently tattooed in your brain. There's a divergent series.
Divergent.
The 1 over n squared series we just looked at, which was less than 1 over x squared in the integral, that was convergent, right? Because it was smaller than the convergent function. This was convergent. 1/2 was bigger than a divergent integral. So this one diverged. So generally that is the behavior of p series. The behavior of p series is related to the behavior of these integrals. So in calculus 2, you would have learned that these things converge if the power is between or is above 1, and they diverge if you're between 0 and 1. And the same rule applies here. P series converge for p greater than 1, strictly greater, and they diverge for p, kind of a dumb way to put it, but let's say p strictly between 0 and 1. If the power is 0, you're just adding a bunch of 1s together. That can't possibly add up to anything, right? But this classifies when series that look like this converge or diverge. This is incredibly important and will continue to play a role in the rest of this chapter. Okay, so p series are something you're supposed to be able to just look at and see if they converge or diverge. You don't have to prove it. You just say, oh, p series with p equal to 2, convergent. Sufficient answer for a question like that.
Can you clarify the 1 over square root n problem with the,
Yes.
the boxes?
Yep.
I'm still a little bit hung up with the areas getting changed to vertical versus horizontal.
I mean, in the last problem, what we did was we built rectangles where we were using the heights with the right end point of the sequence. We were just saying, oh, well, now put the rectangles on this side. That doesn't give us any information in this case to interpret it this way, because interpreting the series as an area of rectangles that fall below something that goes to infinity doesn't tell you anything. So all I'm doing is I'm saying with the green rectangles, I'm saying interpret these as areas of rectangles where I'm using a left approximation for the function. Put the height of the rectangle on the left side. And then in the previous one, I just put the height of the rectangle on the right side. The
Okay,
only
so
thing
it's
that
just
changed was
whether
the
it,
location of the rectangle.
okay, so it was just a like tended to infinity versus like 0 type deal.
Yep.
Okay.
Okay. Is that cool, series? All right. Get the P series stuff in your heads, because there's a whole chapter on the comparison tests that are going to deeply require that you understand how P series behave. Actually, right now, before we go any further, can you tell me about series that look like 1 over the natural log of n? So I just want you to speculate. I'm not gonna prove this right now quite yet, because we're not quite ready, but we're almost ready. Can you tell me? I would like to know if what you think the deal with this series is. Not log p, log n. Now it's not a p series, right? It's not a p series because it's not n to the p for some power p. What do I know about the behavior of natural log versus the behavior of polynomials? Like the natural log of n versus n to the p. What grows faster? N to the p grows faster. So what can you tell me? So that means the natural log of n is less than n to the p eventually, right? Or if you fix a p-value, that's just a true statement. N gets large, that statement holds. So what can you say about this statement? Yeah. If I take reciprocals, I reverse the inequality, right? If this number is smaller and this number is bigger. When I flip them upside down, the bigger number turns into a smaller number. This was 10 and 100. 1/10 is bigger than 1/100. So the terms of this series are bigger than the terms of that one. In particular, the terms of this series are bigger than the terms of that one. So does that series converge or diverge? Diverge. Why? This series is bigger than something that diverges, right? The same argument you're using with these integrals. This series is bigger than that series because these are bigger than those, right? It's the same idea. Because these terms are bigger than those terms, that goes to infinity. It forces that to go to infinity as well. So one of the ideas that's going to come up regularly in here, I mean, this is one of the entry points to the comparison test, which we'll talk about next week. But the idea is the integral test lays the groundwork for the study of much more exotic series. So what does the integral test actually say? Let me get it correct in textbook language here. I'm not lying to you. Oh, there's a bunch of crap we skipped. Did any of you guys have to do conic sections in your calculus 2 classes? Like any chapter 10 stuff with conic sections? What a relief that is not to have to do that again. Okay. Okay, so here's the integral test. All right, now all of these things matter because we have to have a function we can actually integrate. So suppose that f is, and here comes a whole lot of conditions, continuous, positive, decreasing. So notice here, the reason that we have to say all these is because this dictates the kind of sequences I can apply it to. Okay, all of these conditions mean I can't apply this, for example, if the series alternates in sign, positive and negative. This isn't going to apply. We have to have a squeeze theorem running in the background, which means we need to have functions that are continuous, positive, and decreasing. And then this is kind of artificial, but like defined on the interval from 1 to infinity. Really, this could be from any point, 2, 3, 4, it doesn't really matter. And let an be equal to f of n. So the idea here is we start with a function, we build a sequence from the function. So in the context over here, this is the function that gave us the sequence 1 over the square root of n, right? The function gave us the series. Then this is convergent. The series an converges. You guys know if and only if. Could I write IFF? Is that fair? If and only if the integral from 1 to infinity of f of x dx converges. So they're glued to each other. The convergence of the series happens precisely when the improper integral attached to the function exists. That's squeezed in at the bottom of the board. Let me look it up so it's easier to read. The sum from n equals 1 to infinity of an converges if and only if the integral from 1 to infinity of f of x dx converges. I should say, I'll be more precise here, say converges. I mean, it's going to be less than infinity because the function is positive. So that's our first tool for testing a series where it doesn't tell us what the answer is. It doesn't tell us what the limit of a series is. It just tells us whether or not it actually exists. Okay, so this is called an existence theorem. Doesn't tell us what the answer is. In fact, in general, this is a bit of a caution here. In general, the sum from n equals 1 to infinity of an is not equal to the integral from 1 to infinity of f of x dx. They are not equal to each other. It's just a test to see if this adds up to something. If you want to know what that something is, you got to be way more clever. So it gives convergence, but not value. Typical applications, what happens is you get something like this, and as soon as you know something converges, you can use a computer to estimate what the object is that you're looking at. But even in the case of computers, it's easy to get tricked sometimes into thinking that things are convergent that aren't. Because there's functions that are really, really, really slow. It's like the natural log. I saw a computer science paper one time that had that inside of it. The log of the log of the log of n goes to infinity. Pretty damn slow. Okay. So the purpose of these convergence tests is to tell you, yes, it's converging. So whatever you think your estimate is correct. All right, so let's do an example. Not a P series. Well, that's a good one. Okay. All right. So, example. Sum 1 over n squared plus 1. Oh, crap. Just by putting a single plus 1 into this problem, I've broken it. It is no longer a P series. Plus 1 broke it. Now, just based on the ideas of orders of growth, do you think this converges or diverges? I want you really to think about this when you're looking at a series. When you look at something like that, you should have an idea before you do anything if it converges or diverges. What does it look like that series should do? Why? Yeah, but if we let n be like a trillion, then the plus 1 isn't really doing anything. And it looks like 1 over n squared, right? It looks like a P series with P equal to 2. So we should suspect that this converges. I suspect that this converges. Because it reminds me, here's a precise mathematical term, because it reminds me of the sum of 1 over n squared. I mean, that sort of intuitive stuff is I really want you to try to do that when you see these things. If you go in blind, it's easy to get misled by the answers that you come up with. Right? So how do I do it? Well, it's not geometric, and it's not telescoping because that doesn't factor. It's an irreducible. They've chosen this specifically so it's an irreducible quadratic. So unless you're going to go into the land of telescoping series of complex numbers, which probably nobody in here wants to do, it's not telescoping. So we got to do something. So I say, well, are all the terms positive? So I have a little checklist. Is 1 over n squared plus 1 always positive? Sure. Is f of x equal to 1 over x squared plus 1 continuous? Yep. Can't put anything down here that makes an asymptote, right? And finally, what's the other thing we need? Oh, is it decreasing? Does f of x equal to 1 over x squared plus 1 a decreasing function? Now, there's a formal way of showing that it's decreasing and an informal way. The informal way is you put it into a calculator and it looks like it's tending to 0 as like uniformly or monotonically as n goes to infinity. That it's decreasing. Or you could take its derivative and show the derivative is always negative. Right? But to apply the integral test, you have to check all 3 of these conditions hold. Okay, since the answer to all these questions is yes, I can use the integral test. And that means convergence of the series is the same as convergence of an improper integral, which is partly why you were taught the improper integral chapter. So I'm going to use the integral test. I'm going to integrate from 1 to infinity, 1 over x squared plus 1 dx. Now, there's not a single person in here that would ever use infinity as a limit of integration. That would be a sin. You always would know that the first thing you should do when you see an improper integral is to rewrite it as a limit, because there's actually no such thing as this integral. It's really secretly just a shorthand notation for this limit. What is the integral of 1 over x squared plus 1? Arctan. Arctangent of t minus the arctangent of 1. Do I care about the actual value of the arctangent of 1, or I just care it's a number? Just a number, right? Who cares? The integral doesn't tell me anything about the value of the series. I just want to know if this is infinite or finite. That's a finite number. Okay, cool. Arctangent of 1, that exists as a number. What is this limit? Now, if you did not have this forcibly pounded into your brain in your previous class, this limit comes up all the time in calculus books, because it's an example of a function with a horizontal asymptote that is not a polynomial. So what is it? Nope. Pi over 2. Arctangent looks like this. It's tangent tipped over, right? And the asymptotes of tangent are at pi over 2 and minus pi over 2. So the horizontal asymptotes of the arctangent are pi over 2 and minus pi over 2. So this is pi over 2 minus 1. Now, what does that tell me? I did the integral and I got a finite number out. Does that mean that that series adds up to this number? No, this doesn't tell me anything about the value of the series. What it does tell me is that the series does add up, because the integral exists. Then that means this thing converges, because the integral from 1 to infinity of an dx exists. The integral test tells me if that integral is not infinity, this series added up. If that had turned out to be infinity, that series would have diverged instead. So the integral test is a perfect correlation between the integral existing and the series existing. Now, I don't actually know what this adds up to. You can put in a calculator and figure it out if you want. Okay? But this is the sort of trick we're going to be using here. It's applying tests that give us qualitative descriptions of if it converges or not, but not quantitative ideas about what it actually converges to. Yep. So that is called the comparison test. So when you're your idea of eyeballing it, there's a whole chapter coming up, either 11.4 or 11.5, which says, okay, this one, 1 over n squared plus 1 is smaller than 1 over n squared, and 1 over n squared converges, so 1 over n squared plus 1 converges. Absolutely, that is mathematically correct to say that. And like I said, that's called the comparison test. It's just that often I can make this hard to do that for, because I can do something like, plus n minus 10 or something like that. Right? Well, you can use the integral test on this too, but you have to do it more cleverly, because this is a partial fractions problem or an inverse trig function problem. Okay. So yeah, so you should expect in this chapter that you guys are going to have to pull in the knowledge that you learned through your integral methods, because that's the way math books work, right? They taught you how to do integrals, and now they're going to give you a whole bunch of examples to ask you if you remember how to do integrals in the context of series. All right, so that is basically the content 11.3. What we'll talk about next time is we'll do some more examples on Monday of integral test type applications, and then we'll move on to start talking about the comparison tests. Okay. So 11.1, 11.2 are due tonight. If you get a chance to work over the weekend on 11.3, you have all the information you need to get started, but that is due next week. Okay, 11.3 is due next Friday, not this one. We'll talk about it more on Monday. Have a good weekend.
Thank you.
Thank you.
Thank you.